So the key property of the gradient is that the gradient is the vector, it gives you the vector that points in the direction in which the function increases most rapidly. All right, so that's what makes it so useful. Now, let's just look at a couple things. First off, direction. In this class, a direction is always a unit vector. And a unit vector is a vector whose magnitude or length is equal to 1. Okay, now if that seems strange to you, ask yourself, okay, if we were in R2, what does the set of all vectors of length 1 look like? And they're these ones, the unit circle. If we're in R3, what does the collection of all vectors of length 1 look like? Well, they're exactly the points on this sphere. So directions are unit vectors. Okay, so now let's write something blazingly obvious. Okay, so if I've computed the gradient of f and I evaluate it at a location A, so A is some vector in Rn here, then I can write this as magnitude gradient of f times gradient of f over magnitude gradient of f. Now, I said this is stupid obvious because if you just look at the right side and go, oh yeah, they cancel, and sure enough that both sides are equal. Okay, so that's fine. So I guess I should stipulate that this is at a point where the gradient of f is non-zero. I can write this expression here. Okay, why is it useful? Well, it's useful when it comes to the interpretation. So this first part here in parentheses is the rate of fastest increase. So in other words, if you go in the direction in which f is increasing the most rapidly, that is the rate that it's increasing at. Then the other part is this one here in the blue, and that is the direction of fastest increase. So, and the fact that it's going to be a direction, in other words, the fact that it's a unit vector, well, if I take any vector v and divide it by its length, then the resulting thing is going to be a unit vector. And I can tell because if I take its magnitude, then there's a rule about magnitudes that says you can take a scalar outside, and in particular, the scalar that I'm looking at is 1 over magnitude v. So I can pull this guy outside the absolute value bars, or the magnitude bars, and all I'm left with inside is v, and then clearly these guys cancel, and I get 1. And so what that's telling me then is that v over norm v is a vector of length 1. And so that's exactly the kind of thing that I've got going on right here. I'm taking the gradient and dividing it by its magnitude. So I get a direction. So it's a unit vector. Okay. So meditate on this fact. It is very useful. It's telling us that we've got the rate of fastest increase times the direction of fastest increase. Okay. So suppose we want to actually work out an example. So let's look at, we'll take the function f to be x times e to the y. And we'll look at the point a, we'll take a to be coordinate 2, 0. So that's our input vector where we're going to evaluate this function f. At this point, which way do we go to make f increase as quickly as possible? And so the answer, we find the answer to this by computing the gradient and then evaluating the gradient at this point. So we compute the gradient, and the gradient of f is going to be, let's see, so if I take the x derivative, I get e to the y. If I take the y derivative, I get x e to the y. Okay, boom. Okay, so here's a picture of what this guy looks like. So here's the x-axis increasing that way, and the well, I guess it's drawn out here. Y-axis increasing that way. Okay, so we take our gradient f, and then we evaluate the gradient at this point 2, 0. And so we have e to the 0 is 1, and then we have 2 times 1 for the other one, so we get the vector 1, 2. And so then that's telling us that, let's see, so if we find the corresponding unit vector in this direction, then we have grad f over square root 1 squared plus 2 squared. So this is going to be 1 over root 5, 2 over root 5. All right, so now if we go back to our figure here, so I've highlighted here, this is the location 2, 0. Maybe I should label it. And so then you can see that we probably want to go from this starting location. We want to make the value of f increase as rapidly as possible. We probably want to go in that direction, right? And sure enough, the formula that we found is the vector 1, 2. So that would be 1 and then 2, but then it's normalized by root 5. So if we divide that by root 5 to get a vector of length 1, then we'd get, I guess, something like that. So it's saying go that way, and you'll increase the value of f as rapidly as possible. And so if I've drawn this correctly, it should look like these points on the green. Well, okay, so I've drawn it like crap because the green does not look like it's part of the orange surface, and it definitely ought to be. So maybe I should fix that a bit. Okay. Swoop. Okay, there we go. That's the direction that you'd go. So this is the direction that you'd go in order to make the value of f, the height of the surface above you, increase as rapidly as possible. Okay, now what is this rate of change? So how fast is f increasing when you move this direction from A? Well, that's going to be the magnitude of the gradient at this particular location, which we already computed. It's the square root of 5. That's actually what we were computing right here. So we've already got that done. So it's increasing at a rate of square root of 5. Okay, so now how fast is f changing if we if you move towards the point 1/2, 2, instead of going in this direction that we just found? Okay, that's a question we don't know how to answer yet. In order to understand how fast the function's changing as we move in some other direction, we need what's called the directional derivative, and that's the subject of the next clip.